Now. Yeah, so the point that I was trying to make is that this is very more specific way of biasing. This doesn't happen in BJT. In BJT, it's always exponential. So you are not going to get this G30 point. But the other ones are, I mean, this you can do it for BJT, the feed forward one, you can, even this one you can do for BJT because you have a complementary device available and so on, right? Feedback obviously is ubiquitous, you can use for any element. Okay, fine. I mean, I will share, what I'll do is I'll share a paper, go through that fairly easy read. It's a tutorial paper meant for collating all the possible ways of linearizing your LNA. Feel free to use any of them that you in your projects. Okay, fine. So that is as far as discussion on distortion was concerned. Any questions before I move on to an actual LNA problem? Huh. Huh. Sure, yeah. Yeah, it's going to be the case because your GM is also a function of voltage, right? Ideally, you want the GM to be constant, right? But if your GM is also a function of the input, then naturally you have distortion that comes out because GM times V in you want to be linear. If GM is also a function of V in, then GM times V in is not linear. That's the root cause of distortion. Even if it's a small signal, I mean, what is small or is large? We are basically choosing to neglect the others, right? So all of them are always there, right? So given that they are there, we would like to characterize how much of distortion levels we have. Again, these are weak distortion, which means that the fundamental is always much stronger than the others, right? Now, instead of simply, I mean, in 610 or in analog circuits 101, we choose to neglect them. What I'm now saying is that when you make a real product, you cannot neglect them. Yeah, bring them in the picture and see what effect it has. Right? Even though small amounts matter, even if it's like 100x lower, it will still matter. Yeah. Okay, fine. Also, I mean, maybe another point that I should make before I move on is all of these I have talked about are generic, right? In the sense that you can use it for single-ended, differential, and so on. But when I said when I chose to neglect the second order distortion, I automatically assumed you are using a differential circuit, right? Because in a single-ended circuit, you are going to have a single nonlinear circuit, you are going to have G2 V in square also, right? So which means that you need to have some of these, for example, this topology is strictly true for differential architecture. However, this one is true for single-ended also, right? So given that differential architectures are often widely used, we would also like to know that how to get from a single-ended input to a differential output, or single-ended input to a differential input, given that your antenna is single-ended, right? So what I'm saying is your antenna is single-ended, and let's say you have an LNA which is expecting a differential input, right? So an obvious thing to do is to use a balun or a transformer. If they are perfectly balanced, then you are going to get this is VI. Based on the turns ratio, I assume the turns ratio is 1 over root 2, right? Or root 2. So in that case, you are going to get VI by 2 and negative VI by 2, right? So similarly, you can play around with the turns ratio. I mean, as long as the output phase is differential, it's all good, right? So then you have a differential way of getting the signal through, right? So at times, these balance are difficult to make on chip, especially at lower gigahertz frequencies, inductors, bulky. So they are kept off chip also, right? So that's not an issue. So now that you have a differential signal, right? So now the question is, we have, I'll not talk about that part I was introducing. I'll talk about in mixer. So let's now shift focus to an LNA design, right? So we have been teasing about this LNA for a while now. We did a bunch of analysis, talked about all the metrics that are important in an RF amplifier. So now we have the framework. Now that we have the framework, we can quickly go through what are the possible ways of designing an LNA. So now, what are the requirements of LNA? Can you quickly tell me with regards to a design? What are the things that the LNA needs to be mindful of? Or pardon? Noise figure. Okay. So low. Obviously, it is embedded in the name, like low noise amplifier. So low noise figure. What else? Linearity. Okay. Good linearity. Because ultimately, it is sitting just next to the antenna. It can get a lot of, various amplitudes of input. Given that you have maybe a SAW filter upfront, still within the band you can get fairly high, different types of, different amplitudes of input, right? What else? Come again? Impedance matching, basically matching, right? So that is very specific to an LNA because it is seeing something which is coming from outside the chip, right? So without matching, you have a big problem. So matching. Anything else? That's all. Obviously, another thing is gain, right? You would want gain. It's an amplifier, right? So you cannot forget that, right? So you want gain. Fine. So now let's tick off one by one. Since matching is very in IC design where the entire receiver is sitting on the chip, matching becomes very critical to an LNA. It's not very critical to other blocks if all the blocks are sitting on the chip after the LNA. So matching becomes critical for the LNA. Input matching rather, I should say input matching. If the rest of the receiver is not on chip, then output matching also becomes important. Okay. So now tell me, how can I go about doing an input match? Given that we'll assume that the antenna is a perfectly 50 ohm. And the simplest transistor that I can have is, I would like to start off with a single transistor circuit, right? Because more number of transistors, more problems. Common source, okay. So if I have a common source, and I'm not showing biasing, right? And let's only concentrate on the output current. Will this have matching? Yeah, so you have to put a matching network. What is the simplest way of matching that you can do? Before we put a matching network, what is the simplest way you can match this circuit? So this is inside the chip, this is chip. And you have long lines here. Yeah, you can say, yeah, you can have a resistor of 50 ohm, right? Yeah, so okay, I'll come to inductor to cancel the CGS, but let's stick to this. This is going to match, no issues, right? If you have a CGS, as he's pointing out, if you have a CGS here, so then at high frequencies, obviously it's not going to match. Then maybe we can have an inductor here, right? To resonate out that CGS, right? This is going to work, but now look at the specifications of LNA. Which one do you think is going to suffer, or all are good? Let's not discuss about linearity for the time being, right? So noise will be a problem. The noise matching is a problem, right? So noise of the resistor directly comes out. Why? Because ultimate, I mean, you cannot do anything about the noise of this guy. This will always be there. So in the noise factor, the 1 plus, the 1 is basically the noise due to RS. The plus whatever is the additional. Now, if you have this another RS here, another R which is equal to RS. So this will contribute exactly the same amount of output noise as RS, right? Which means your noise figure doubles, correct? So even though this works at a penalty of noise figure. What else? What other topologies do you think can give me input matching? Pardon? Instead of going for resistance, go for what? I introduced a lossless matching, right? I introduced LNC. But the real part has to be there, right? Lossless part, lossless elements do not have the real part. So what about common gate configuration, right? You are doing the assignment, it has a common gate configuration. Okay, fine. So if you have a common gate, so the reason common gate is also useful is because, again, biasing not shown. You do not need a separate matching network, explicit matching network. I mean, you can obviously design because the noise match is not the same as power match. But in principle, you don't need a explicit matching network because as long as the input impedance here is equal to RS, you are good. What is that? It is approximately equal to 1 over GM. And if you want to improve GDS, basically it's 1 over GM plus GDS, right? So as long as you ensure that 1 over GM is exactly equal to RS, you are good, right? But what about the noise? Why is it moving around so much? Okay, keep my hand steady. What about the noise? I am interested in the short circuit current. So I'm assuming 1 over GM is equal to RS. This is for match. So what will be the effect of noise? So obviously this guy, the current due to, I mean, let's say this RS has a noise voltage equivalent Vn. So this current will be how much? Vn by 2 RS, right? Because it is matched, so impedance here has to be RS. So effectively, it's VNC is 2 RS. So Vn by 2 RS, Vn by 2 RS will be the current. That flows into the short also. It flows here. So what is the contribution of IN? It will be IN by 2. Why? Because the current that comes here, it can go either to the left or to the right, but it is identical impedance because it is matched, right? So it will split equally between top and bottom. So naturally, the output will also be IN over 2, right? So the contribution is identical between RS and IN, right? So again, you get close to and doubling of noise factor. I'm saying close to because this IN, spectral density of IN is 4 kT gamma GM, where the spectral density of RS is 4 kT by RS. I mean, if I see the current spectral density, right? So this gamma is not exactly 1, it is 2/3. So you kind of get a lower addition of noise. With the previous case, you were getting exactly twice. Here you will get lower. So you can get less than 3 dB noise figure. And if you do, yeah, so I mean, in principle, you are going to get higher because I have not shown the biasing network, right? So you are going to have some biasing network here, some current mirror and all those things. They are also going to contribute current, but you can probably reduce the effect of those currents by designing your matching network for a noise match channel, right? So that's the part of the assignment. Okay, so still fairly high noise figure, right? But still works. I mean, by the way, when I'm not disregarding any of these configurations. There are applications where you need maybe 6 dB noise figure, 4 dB noise figure. There are applications which are not very noise sensitive. For example, when you use your remote controls, right? Or even now everything has a remote which you can control an AC, fridge, TV, everything, right? So single remote does everything. Their noise figure requirements are not that high. So you can use the simplistic configurations which save power also, because more circuits you have, more power consuming. Your bulky, your not only bulky but more power hungry your system becomes. So you don't need to. You can save power and in lieu of noise, right? So, but if I have to go for a noise network which gives me sub 3 dB noise figure, that is, let's say 2 dB noise figure, or let's say 1.5 dB noise figure, or 1 dB noise figure, then clearly these type of circuits are not going to work. Why it is fundamentally why it's not going to work? Because you are in order to match, you are trying to introduce another element which is also noisy, right? So if that is the problem, then the solution cannot be any of these type of topologies. Now, to appreciate what is the alternative solution, I would take a detour and show you one topology which is generic, nothing to do with the transistor per se, right? So let's say you have some block which has a transfer function Hj omega. So at omega naught, you are going to have some mod of H and some angle, right? Typically, it's a phase lag, right? So if you can have also phase lead at some certain frequencies, but let's assume phase lag. So you're going to have mod of H e power minus j5. Okay. So, and let's say I introduce a capacitor similar to a Miller effect, right? So I introduce a capacitor here, and let's assume this impedance is infinite, right? Nothing goes in to H of j omega. So what is the impedance that I see? I want to find out this impedance, right? So, I mean, just like Miller, what I'll do is I'll find out the current through the capacitor. So this I will be equal to j omega c times the voltage across the capacitor, which is V in plus V in minus V in mod of H e to the minus j5, right? So which essentially means j omega c, so I by V in is j omega c 1 minus mod of H e power minus j5. If I split e to the power minus j5 into cos phi, say sin phi, so I get 1 plus cosine phi plus j mod of H, right? I missed here. Mod of H sin phi. Right, 1 minus, right? Yes, correct. Sorry, 1 minus here. Yeah, 1 minus cos of H, and here you are going to have plus, right? Okay, so now if I split this, what you see, you get a imaginary component, which is j omega c, 1 minus mod of H sine phi, and then you get a real component, negative in sign, but you get a real component omega c mod H sine phi, right? So note that this real component has come up without the use of any resistor per se, right? Now you might say, how have I manufactured H? We'll come to that, right? So, but there is a real component. Now, don't concentrate too much with the fact that you have a negative value to it. It can be either negative or positive based on the value of phi, right? So if there is inversion, between either side of H, then that real component becomes positive. If you don't have inversion, that becomes negative. The key thing to take away is that you can get a real component, and based on your requirement, it can be manufactured to be either positive or negative at a certain frequency, right? Not across, the value will be constant for a certain frequency. And whenever you can find such scenarios, then it becomes useful for narrowband applications. Because in narrowband, if something happens at a particular frequency, within that, around that frequency also, we can assume it exists. So if now let me introduce another concept here. So what are we essentially saying? If there is a phase lag or lead, if there is a phase difference between two events, two electronic events like voltage or current or whatever, I took the case of voltage, and I put a capacitor, or for that matter, I can even put an inductor, then it's possible to get a positive, it's possible to get a real part, right? So why are you doing all these things? We're doing all these things because ultimately we know that the best amplifier that I have is a common source amplifier, not a common gate, nothing. We want a common source amplifier to get gain. Right? Nothing else gives gain. So we want a common source. And we also want matching. Okay. If I connect it like this, doesn't give matching. I have to put additional R and all, which I don't want to do because of noise issues. So what is this telling us? This is basically telling us if I identify another point in this network, which has some delay with respect to the input, and I connect a capacitor between that point and that delayed point, then possibly I can get a real term, right? So what is the important thing? In this case, the variable of interest is the current. If I have to draw an analogy between whatever I discussed now and this, all we want is then a delay between V and I. V is the input V, and I is the output I. Correct? So if the V instantaneously comes here and this is grounded, then there is no delay between V and I. Assuming transistor instantaneous, then GMVI is instantaneous. So I want to delay I. V is input. So I want to delay I. How can I delay I? Putting a cap at source won't delay I, right? Because instantaneously cap is shorted. Inductor, right? I can put an inductor, right? So I can put an inductor here. So it will delay I, right? So now all I do, if I put a capacitor between these two, again, you cannot put a capacitor between a current and a voltage, but all we are doing is that there will be a phase difference between this point and this point, right? In this case, probably a phase lead, because in terms of voltage, it will probably be a phase lead because it is going to instantaneously jump. But having said that, we all need a phase difference. So if I put a capacitor here, and then maybe you do an analysis and find out what is the input impedance of this guy. I think you have done this yeah, right. So you find this in the surprise quiz that we had. I'm not sure how many of you were there. You found out the Z in here. Yeah, right. So how do I find out? So let me do it for you today, because since we are officially doing this. And this topology is one of the bedrocks of all LNA designs, almost all LNA designs for narrowband applications. So I apply a V, then I have to find out I. This I clearly goes through the capacitor, right? Because I assume that, this capacitor, by the way, anyway exists because it's a CGS, right? So it develops a VGS of I by J omega CGS, right? So this current will be GM times I by J omega CGS, right? So this voltage will be this voltage is essentially V minus I by j omega CGS, which is equal to the total current times j omega L, right? So total current is I plus I into, this is I and this is the other current. So I 1 plus GM by j omega CGS times j omega L, right? So if I break it, this becomes V is equal to I 1 plus 1 by j omega CGS. Sorry, not 1 plus. This is, so this guy comes in, becomes 1 by j omega CGS plus j omega L, plus this term gets multiplied with this term, you get GM GML by CGS. Right? So clearly you get a positive real term without the use of any explicit resistor. Right? And at a particular frequency, you can manufacture these to resonate. The CGS and the L, you can manufacture the L to resonate out the CGS, right? So at omega equal to 1 by under root L CGS, your V over I becomes absolutely real. And if you make this to be equal to RS, then you have a match. Right? Well, yes, in principle, but I wouldn't say that also. His question was, looks like L and CGS values are fixed, only GM we can change. That without, since I have not introduced any other concepts, even that is not strictly true because CGS and GM are related. I cannot arbitrarily increase GM without changing CGS, right? So in fact, this you will see that this is often written as GM over CGS is omega t, right? The transit frequency, 2 pi times the transit frequency, omega t times L, which is equal to RS, right? So this is another way of expressing. So it looks like the only thing you can control is L, because ultimately you would like to bias your transistor with a maximum omega t, right? I would elaborate in the next class what other impacts are there if you do not. But at least from the perspective of distortion, right, you would like to ensure that your overdrive is the maximum. For a certain GM, for a certain value of GM, if you want to make sure your overdrive is maximum, which means that you'll have to ensure that it is biased at maximum omega t, maximum FT. Why? Yeah, right. Your W by L has to be minimum, which means CGS is minimum, right? Which means naturally you are biasing the maximum possible omega t, which means even though omega t might seem like a design variable, it often is not. But L is a design variable, right? But you might think that in this case, if I change L, the center frequency is changing. But I am saying that CGS I will not be able to change independently, but that's not true because you can change CGS provided you are okay with changing GM also. Basically, you have to keep omega t constant, right? If omega t remains constant, if you have one circuit and you copy and paste the same circuit again, your omega t doesn't change, but the input impedance doubles. If it's in parallel, it halves, or CGS doubles, right? So you can basically scale up and down CGS. So this works, but it has certain, the vanilla this circuit has certain limitations, right? We'll talk about that in the next class. Before we end, any other questions? Okay, fine. We'll stop here then.